Do we just want to,
Wait another 2 minutes or so?
well, I don't know. What do you think, Adam?
I'm the wrong person to ask. I always start my talks late, and then I start them later the next time because that's just, yeah.
Maybe we'll just get going because when people come in, I'll be finishing up and then they can catch
Sounds
up.
good to me.
All right. All right. Well, welcome everyone to the Q Discovery webinar. This is our first initiative of the Quantum Discovery Program, and we're looking at quantum computing for decentralized energy. Just a quick background, I think quite a few of you have maybe never heard of Decentralized Energy Canada. We are a national industry association that's dedicated to decentralized energy. We define decentralized energy as, hello, Jeff. A little camera pops up and on. Yeah, camera's off if you could, please. I think we're expecting about 50 or 60 people, so it'll get a little busy on there. Anyways, for those of you that don't know what decentralized energy is, the best way to think of it is energy integrated into the built environment. So whether that's into a community or into a building. So right now we have, some buildings have backup diesel generation for when the grid goes out. Decentralized energy can be distribution connected or off grid. It can also be transmission connected if the generation is built for load. So if you're generating that energy to take care of a certain local load or number of loads on one feeder, that's decentralized energy. The off-grid applications are usually rural or industrial. So if you have in-field equipment that has solar and battery running it, that would be a decentralized energy application in the industrial sector. And the most important thing is that you're integrating your energy close to where it's being used. So you're saving on losses, you're increasing reliability. Most of the time it's in the form of a microgrid. So you have a number of technologies meeting the energy need, and it can include thermal as well. So heat pumps are increasingly important in our world. So what's providing your heat and cooling, what's providing your electricity is all integrated into that built environment. So Decentralized Energy Canada, for its members and the industry, we've been around for 22 years now. And it's been an interesting journey, but right now it is pretty hot. And I think a number of reasons have made this the case. We have extreme weather that is making our infrastructure vulnerable to wildfires, tornadoes, ice storms. We've always had that, but with increasing occurrence now. The price of electricity is increasing, and the cost of transmission infrastructure is quite high. So there are cost benefits to integrating your energy systems into the built environment. So, one of the initiatives that Decentralized Energy Canada is working on right now is the Energy Innovation Challenge. The first edition has been with the City of Medicine Hat, and we're halfway through that, demonstrating real decentralized energy innovations like energy storage, predictive analytics, building management systems in a real distributed network environment, which is the City of Medicine Hat's distribution network. The next phase of our Energy Innovation Challenge is the Quantum Edition. So we are looking at quantum technologies, quantum computing, quantum sensors, and cryptography for increasing security of systems that use quantum-ready technologies. And just to give people a bit of an idea of the use case scenarios, advanced metering infrastructure is a very popular topic in the quantum technology space right now. And the reason for that is the complexity of that and the number of data points that you have in advanced metering. And across Canada, many utilities are in a very stressful place right now because they've installed smart meters and advanced metering infrastructure, but all this data is coming in and they don't really know what to do with it. And there's a number of reasons for that. Their staff doesn't have the right skill set for working on that data. The data is not in the right format for advanced computing. So we want to start taking a look at quantum computing compared to traditional computing. What are the good use case scenarios for quantum computing, and what scenarios are still good for traditional computing, and other innovations will be in that space and with time. So the objective of this session Adam Benny Watts from Quantum City will be giving you an overview of what to expect from quantum computing for decentralized energy. We will have questions at the end, if you can use the chat box for Q&A. If we get into a good dialogue, we are going to unmute some people for a bit more of a fluid discussion, but it just depends on the volume of the questions. We're just going to play that by ear, but if you can hold your questions till the end. And I just want to thank our partners. Alberta Innovates has been supporting this initiative, and we're thankful for that support. Quantum City is our near and dear partner. So they're in the Alistair Ross Centre, and Decentralized Energy Canada is in the Alberta Innovates Centre across the parking lot. So it's very ideal. And also a thank you to the University of Calgary. So with that, Adam, I will hand it over to you and mute myself unless there's any other things I have missed.
I think you covered all the ones I had on my list.
Excellent.
All right. Yeah. Thanks, Anouk, for the introduction. Hi, everyone. Let's see if I can smoothly share screen. Yes, I can. Beautiful. Yeah. So hi, everyone. Excited to be here. Thank you all for coming. Thanks, Anouk, for the introduction. And this talk, it's going to be sort of first, mostly a high-level overview of quantum, but sort of with an eye towards quantum computing, but with an eye towards applications. And then at the end, I'm going to try and say things a little more focused towards decentralized energy and applications in that space. But before any of that, I'm going to just use 2 minutes for advertisement. So I'm here, like Anouk said, on behalf of Quantum City. What is Quantum City? It's an initiative within the University of Calgary. And our goal really is to be an ecosystem builder, both inside Alberta and across Canada. So we're trying to sort of build the quantum ecosystem. And we're doing this mostly by focusing on non-quantum end users and helping with that adoption piece. So finding industries that might one day benefit from quantum technology generally, although this talk is going to focus on quantum computing, and helping scope out first projects, understand the landscape, understand where quantum might be useful and where it won't be useful. And then me, I'm Adam. I'm a scientist in residence at Quantum City, which means that I have an academic background. So I was a grad student and then a postdoc, studying some fairly theoretical aspects of quantum computing. And now my job is really to be a bridge between the academic research that goes on and some of these real world potential applications of quantum computing now, and especially the ones coming in the future. So that means that I still have my own research. I have some industry focused research, and I'm also engaged in outreach and sort of not even research focused, but just scoping out projects, understanding the landscape, helping industry adapt. And so it's quite a fun set of problems that I get to work on. But okay, that's it for the advertising. We can get into the talk. And I want the talk to be practical, but I have a theorist background, and so I'm going to have one slide where I just want to make the high-level case for quantum computing, because I can't give this talk without saying it. So where to start? I want to think about classical computers just for a second and say that classical computers, the computers that we know and love, use today all the time, they're good at simulating classical mechanics. So if you've got a physics background, you probably know what I mean already. If you don't, they're good at simulating the world we see around us. If I look at a classical computer, I can predict whether or not a skyscraper will stand or fall. I can understand an airplane and predict whether or not it's going to fly before I build it. And if I look at natural phenomenon or electricity and magnetism, these sorts of things, they can also be simulated. They can also be handled by classical computers. Now, a consequence of that fact, and this gets slightly technical, but I just want to tell you the consequence, is that all classical computers can do about the same thing. And now the technical reason for that is that if you have computer A and computer B, computer A can always just first simulate computer B and then solve whatever computer B can solve. This is like how I can run a Mac emulator on a Windows computer or vice versa. And so, of course, some computers are better, some computers are worse, some are faster, some are slower. But the set of problems that you can solve with a classical computer are all about the same. And, in the complexity theoretic world, we make that formal, but you don't have to. You can just sort of say that the set of problems out there that computers can solve are all about the same ones. Now, the next thing to note is that classical computers are bad at simulating quantum mechanics. So when I have a system whose behavior is quantum mechanical, And you can think just a system who's very, very small. When I have two electrons interacting, and I want to make a prediction about what's going to happen next, that's a task that our classical computers seem to struggle with. They're challenged by this. And maybe they can handle 2 electrons, but if I have 10 or I have 100, this problem becomes very, very hard for classical computers. What that means is that if I were to have a computer whose inner workings were quantum mechanical, a quantum computer, there might be problems out there that that computer can solve that classical computers are completely unable to handle. So there's problems that you can only solve efficiently with a quantum computer. Okay, that's the only theory I really want to go through. But there's an important, I say this all for a good reason, which is an important consequence of this is that when we talk about quantum computers, we're talking about computers that can solve a different class of problems. Quantum computers are not just faster computers. They're not just computers with more storage space. They're computers that are really going to be good at solving a specific set of problems. And when you're not in that space, when you're not dealing with those problems, well, then classical computers might be better. You know, they're not out competing classical computers. They're targeting a different set of problems. And it's really key right now across the field to understand what those problems are. And we'll get more into that in a little bit. Okay. So this is the quantum computing argument. And it's been around for a while. I think we normally attribute this idea, this observation, to Richard Feynman, a famous physicist, who gave a talk in 1981 and published in 1982, and the quote's up there. But that's sort of the first iteration of this idea that I just mentioned about building a quantum computer and using it to simulate quantum mechanics. And so this idea, this sort of birthplace of the field, came way back in the 1980s. And I tell you that because now I want to tell you what happens next. So we're going to go through a bit of a history lesson. It's going to be an incomplete history lesson, and the reason I'm doing it is I mean, the history is fascinating, but the reason I'm doing it now is to sort of talk about where we've come, why now is a very exciting time in the field, and eventually so that I can speculate a little about what's going to happen next, which will inform the rest of this talk. But, now we get to go through the history just a tiny bit. So we start 1982, the birth of this field. Richard Feynman gives this talk. It's published with this idea of building a quantum computer. Now, Feynman was a physicist, so he wasn't completely formal. And a couple of years later, David Deutsch sort of really nailed down formally what it meant, what it would mean to build a quantum computer. And he introduced this notion, this language that we still use today of a universal quantum computer. I'm mentioning this because in this history, I also want to expose everyone to some words that are going to show up all over the place. So this is a history lesson and just word exposure, terminology exposure, so that if you go out into the quantum computing space after this, you'll know what some things mean. So back here in 1985, we got this notion of a universal quantum computer. And this is a computer that can process information using the full power of quantum mechanics. Sort of all the operations that we think should be allowed to us can be implemented by a universal quantum computer. So this got formalized in the 1980s. Now, it took a couple of years, but about 10 years later, mid-90s, we had a real breakthrough on the theoretical side. So this notion of universal quantum computer was floating out there for a while, and then theorists really latched onto it and started to prove some of the things that these universal quantum computers could do. Some of the most exciting uses of quantum computers were understood theoretically way back in the mid-90s. Another idea that got figured out then was quantum error correction. We're going to come back to that in a little bit. But this is just an interesting time period because it's when we nailed down a lot of the theory around quantum computing. But at this point, quantum computing was still entirely theoretical, no experiment. That changed a little while later when we built experimentally the first quantum computer. Now, there's another word that's going to show up all the time. I'm going to talk about how many qubits a quantum computer has. That's how many zeros and ones. It's the size of the machine. It's how much information it can process. So it's how many zeros and ones you can feed into the machine and how many zeros and ones you'll get out of the machine at the end. And so we had our first experimental demonstration in the 1998, and we got a 3-qubit machine. So very, very small. Could put in only a small amount of information, could get out only a small amount of information, but still it was something. It was the start of our experimental efforts. The field progressed. We got a little better. We got up to 12 qubits by I guess, mid 2000s. So still very small in the amount of information we can put in and out, but progress. Something else that happened around this time is we started thinking about these things called quantum annealers. And now this is still a quantum machine, still processing information using quantum mechanics, but it's sort of in contrast to this universal quantum computer, it's a machine that solves a very specific task. So it's a machine that's not using maybe the full processing power of quantum mechanics, but it's still doing something quantum mechanical to solve some problems. And now because it's easier to build because this machine is more limited, they're easier to build, and so the problem size was bigger, right? We could handle 84 zeros and ones instead of just 12. But I should say, this is still sort of in the realm of theoretically interesting, but not useful. A useful benchmark to have in your head is if I'm talking about anything with less than 20 qubits, whatever that machine does, it's something that I can simulate on my laptop. And I know I said that quantum computers could solve problems that classical computers couldn't solve efficiently. That's true. But when your problem is small, when you're looking at 20 qubits or less, you're still in a realm where even the inefficient algorithms work. So anything I'm doing with less than 20 qubits is not operationally useful. It's for theory and development and experiment. So from 2006 to 2017, another 10 years, we make progress, but not a ton, right? We go from 12 to 17 qubits on our quantum computers. So the field is progressing, but not sort of at a breakthrough rate. Then you go forward one more year and something interesting happens, right? The qubit counts jump up. We go from 17 to 72. And so this is exciting for a lot of reasons. It pushes us fairly quickly outside the realm of what we can simulate on our laptops. It pushes us into a new era. And I think the 72 qubit quantum computer was a result by Google, by the way. So it's also, start to see industry involvement in the field. And it kicks off this era that is known now as the NISQ era, the era of noisy intermediate scale quantum computers. And so a few interesting things happen. You start to see quantum computers becoming commercially available. You start to see machines on the cloud that you can buy time on with around 100 qubits, right? Safely outside of the simulable on a laptop range. Annealers also progress. So you go from the 84 qubit annealers to, thousands of qubit annealers. So fairly significant problem sizes that you can fit on these machines. And this era is really the era of what's called quantum supremacy. So this made the news. Maybe some of you have seen it in the news, but this is the era where for the first time we see a quantum computer solving a problem that we think no classical computer could solve, or solving a problem that would take classical computers a very, very long amount of time to solve. Now, this isn't a useful problem. It's by design, almost a useless problem, but it's a problem that we think quantum computers are good at and classical computers are bad at. So this is sort of the realization of this idea that Feynman had, I guess 40 years earlier, saying that there are some problems out there that you can only solve with a quantum computer, and you're going to need to build a quantum computer to solve them. So we see sort of an experimental demonstration of this idea from 20 years ago, which is quite exciting. Now, there's also a major limitation of computers in this era, which is this first word, this noisy. So what does noisy mean? It means computers have errors, and I don't want to get too technical about this, but if you think about a classical machine, processing zeros and ones, you can sort of think about a bit flip error where you have a 0, but it gets turned into a 1 by accident. Quantum computers have these same sorts of errors. They also have sort of more exotic errors, but a similar flavor. And the machines that we have available in this NISQ era, they have a lot of errors. So that's what noisy refers to. You've got, when you try and run a computation, you get problems along the way. And so that's just sort of it happens to all computers in this era, and it's a major problem. Okay, but that's not the end of the story, because if we look now in very recent history, I think people are starting to agree that we're leaving this NISQ era. And the thing that's starting to move us out of this NISQ era is we start to see experimental demonstrations of quantum error correction. So the idea here is that I take lots of noisy qubits, lots of these error qubits that do have errors, and I sort of group them together and use this communal grouping to simulate a qubit with a lower error rate. So to simulate what's called a logical qubit, this is another word that you'll see in the future, or maybe a fault-tolerant qubit. And this is a qubit that effectively has no error. So we took the first steps in that direction experimentally, just a few months ago. Progress is still ongoing. And so we're starting to leave this NISQ era and move toward lower error machines. And that's very, very exciting for the field. Now, what I want to talk about is then what comes next. And so I'm going to make some predictions in these next few slides. They aren't my predictions necessarily. They're sort of an amalgamation of various hardware timelines. And I'm going to try and avoid saying anything too concrete about my own personal opinion on these timelines. If I do say something about my opinion, you should ignore me, because I'm a theorist, so I don't know what I'm talking about on the experimental side of things anyways. But I'm going to try and sort of report, collect these results and report them and tell you what they might mean from a theoretical perspective. So what's supposed to happen next? What are the predictions? Well, if we look just a couple years in the future, what we should have happen is the number of qubits that live on our machines keeps increasing. We go from hundreds of noisy qubits to thousands of noisy qubits. So the problem sizes that we can tackle with quantum computers get larger. And there's a very nice piece of branding that comes from IBM. I like the branding, so I'll repeat it here, which is that they call this era the era of quantum utility. So this is when you start to have machines that are not classically simulable. So you have so many qubits that you're at least solving a problem that you can't immediately solve on your laptop the same way. And that problem might be useful. So you might be able to try and solve useful problems on a quantum device. And there might be an advantage there, right? There's the possibility that you're doing something in a realm where you're outperforming classical techniques. And that's sort of what's meant by this era of quantum utility. If you go a few more years in the future, late 2020s, early 2030s, what happens is we keep progressing on this sort of error correction front, and the number of qubits go down, but so does the error. So we start building these logical or these noise-free qubits, these effectively error-free qubits. And so we go back down to hundreds, but now we have hundreds of qubits with no error to play with. And this is my own sort of personal buzzword, but I like to think of this as the era of perhaps quantum advantage. This is where, if we haven't seen it already, I would hope that we start seeing quantum computers, outperforming classical counterparts on some real world problem, where you start to have a quantum computer that solves a problem more efficiently in terms of dollars or time than the classical computers that you could also try and throw at the problem. Okay, and then if you're willing to jump another 3 or 4 years in the future, now you get back to the thousands of qubits, and these qubits are logical, they're noise-free. And this is an exciting era, because this is an era where the things that we know are good ideas to do with quantum computers, where the real breakthrough applications of quantum computers become available to us. So this is the era of exponential quantum speedups. If you think back to the timeline from the last slide, all of these theoretical breakthroughs that we made in the mid-90s, this is the era where they become realizable, actionable, and we can start running them on machines. So at this point, when we have thousands of logical qubits, then we know there are good applications of these machines, and we can go out there and start using them. Okay, and so what's exciting to me as a theorist and as someone working in this space is that somewhere in this next 10 years or so comes the time when we start to see quantum computers really being useful for solving problems in the real world, right? It's this sort of breakthrough point where we find a real world application of a quantum computer where it's the best machine for solving a problem, where there's a real commercial advantage to using a quantum computer, should come in the next 10 years. And so that's exciting. That's going to be a very exciting moment for our field. And I think that's a very good reason why there's a lot of excitement even right now about quantum machines. Okay. And so that's the history. Now, what you might ask, right, is so what's this actually mean? What are the practical applications of this? Let's try and make it a little more concrete. And so this is where I'm not a domain expert, but this is where I will do my best to sort of translate some of these applications of quantum computing into digestible terms and talk a little bit about how you might interact with this quantum computers as the field develops and grows. And so the first thing I should mention, as we think about applications of quantum machines now, quantum computers, is that broadly speaking, there's sort of two regimes you can think about, two classes of algorithms. And this is a taxonomy. It's not perfect, but it's a helpful way to start thinking. And the first class of algorithms you might think about are fault-tolerant quantum algorithms. So these are algorithms like the algorithms developed in the mid-90s, algorithms that work on perfect quantum devices. And what's nice about them is there are algorithms out there where we're pretty darn certain there's an advantage. I said guaranteed, and then I put it in quotes because in complexity theory, nothing is for certain. But you can be pretty certain that these algorithms will outperform their classical counterparts. That's good. What's bad is that these algorithms don't run on today's machines. And in particular, the noise on today's machines, the errors on today's machines, ruin all of these algorithms. These algorithms are elegant, sophisticated ideas, but they're delicate. And if you have a single one turn into a zero somewhere along the computation, the algorithm falls apart and you don't get the answer that you want to get. So they're not yet available to us. There are interesting projects to be done in this space, but the projects you do around these fault-tolerant quantum algorithms are resource estimation type problems, or maybe connecting an algorithm to a real concrete use case, and then waiting for the devices to advance to the point where you can run it. So you can do very interesting work in this space, but the work that you do probably doesn't involve running code on a real-world quantum computer. It involves planning and organizing and understanding, and doing sort of the resource estimates to figure out when this algorithm becomes feasible to you. Okay, and now I'm going to go through just a few examples to give you a flavor. I'm going to do this very quickly, but the talk is recorded. So, if you want to see these, I'm just going to put them up on the screen. And I'm going to say just what sort of algorithms are there. The three big ones maybe. One is, the one that's probably most well known is factoring, right? If you hear about quantum computers breaking crypto systems, breaking cryptography, it comes down to this fact that if I have a number and I want to break it into its prime factors, that's a problem that we think a quantum computer can solve and a classical computer can't. Maybe more useful to some people here are these sort of quantum simulation type algorithms where I want to predict the dynamics of a quantum system. I have a system and its behavior is fundamentally quantum mechanical. It's small enough that I need quantum mechanics to describe what's going on, and I want to predict what's going to happen. And these sort of quantum simulation type algorithms, one day we think will be a use of quantum computers, and they fall into this fault-tolerant regime. Something else that gets talked about quite a bit is matrix inversion, the HHL algorithm. That's down in this bottom right corner. And there are some caveats to it, but essentially you're inverting a giant sparse matrix, and people try and use this algorithm all over the place. So again, this is a place, if this is sort of a direction you want to look at, you need to think about the caveats. You need to think about the resources required, but if you line that all up, then there is potentially a strong quantum advantage here one day. Okay, but what I want to focus on this talk, because it's things that we can run today, are the near-term quantum algorithms, or maybe the quantum heuristics. And so in contrast to these fault-tolerant algorithms that we will run one day, and we know there is a quantum advantage, these near-term algorithms, often there is no guaranteed quantum advantage. There's even maybe no strong theoretical argument that says these algorithms should outperform classical algorithms. But they're interesting ideas, right? They're heuristics that for some reason we think are worth trying on a quantum computer and that might perform well. We don't know. But what we get out of it is that they're algorithms that we can run today on machines today. And the reason that's true is that we designed these algorithms such that they're robust against errors. We design these algorithms so that the output is still interesting and valid and useful, even if I have a 0 flipped to a 1 somewhere along the computation. So, we lose this guaranteed quantum advantage, but we gain the ability to run the algorithms right now and see what happens. Now, very often, not always, and I might have said this by accident already, these near-term quantum algorithms are variational. What are called variational algorithms. I put a picture up that might be too small to see, but the crux of it is that these are algorithms where you have a quantum computer used in parallel with a classical co-processor, right? So I have a quantum computer generating, doing some data processing but the input data and the output data, and even the sort of program run by the quantum computer is all adjusted by some classical co-processing that goes on. So these algorithms are designed with the idea that you get as much as you can out of classical compute, and then you just introduce a small piece of quantum compute alongside and hope that that pushes you a little bit further. And I'm just going to be very clear. Well, I think I'll talk later about sort of parametrized quantum circuits. The idea here is that you've got some quantum operation with a few parameters. These parameters get trained classically by classical pre and post processing of the data going through the quantum computer. So you have some small amount of quantum processing that's going on, but these parameters are tuned according to some classical outer loop of processing that happens. And so that's sort of a very common feature of these variational quantum algorithms that we'll see in a little bit. And then I'm going to return to this buzzword that I like, which is to say that a target, when you're talking about these near-term quantum algorithms, today and in the next few years, is you're looking for something like quantum utility. So especially sort of in this setting where you're thinking of real-world applications of these algorithms, what you want to do is you want to take a real-world problem, you want to solve it using a quantum computer, sort of at a scale that is interesting, at a scale that might be useful. And you want to make sure that whatever you do on your quantum computer, it's not brute force simulable. It's not obviously classically simulable by a laptop or by some amounts of classical compute. That doesn't mean that a classical computer can't solve the same problem, but it just means that at least the quantum computer is using a different approach. You've demonstrated there's a different technique that you can try to solve this problem. It involves a quantum computer. It can solve the problem at some moderate, small, but still interesting scale. And it is, in fact, doing something quantum and interesting. And so that's sort of the idea behind quantum utility. And and for projects in the next few years, that's sort of the target. That's one good target to have in mind, certainly. Okay, and now I'm going to try and end in about 8 minutes or something like that. So we have lots of time for questions, but I do want to go through now some actual specific sort of detailed applications, a few detailed sort of uses of quantum computers. So go through some possible heuristics in a little more detail. I'm going to do this at a semi-technical level. These slides might be more technical than some of the ones that we've seen so far. But yeah, so hopefully, ask me lots of questions about it later. It's going to be technical, but it's not going to be a complete story. So there's lots that I hope to explain afterwards. And I should say that the goal in all of this is that I say enough that it might start to connect with some real world problems that you have in the back of your mind. So I'm going to try and give enough detail that you can start to plug in maybe a real world application or some data that you have lying around that you want to process where a quantum computer might be helpful. Okay, so that's the goal of all of this. But now, okay, so what's an example of a near-term quantum algorithm? What's sort of a flavor of heuristic that you can try on quantum computers? First one that I'm going to talk about are these things called QUBO solvers. Okay, so what is a QUBO? This is a word that existed before quantum computing, or at least was developed independent of quantum computing. QUBO stands for Quadratic Unconstrained Binary Optimization Problem. What does that mean? That means I've got binary variables, zeros and ones, and I've got a cost function that's quadratic in those variables. Right? So I've written both of these two things down here. I think for the technical folks, hopefully that's interesting. For the non-technical folks, we'll get back to the big picture in a sec. But I've got a binary variable, I've got a cost function that's quadratic, and my goal now is to minimize this quadratic cost function. And this framework is very general. There's a lot of problems that you can cast sort of as QUBO problems. If you want a picture to have in your head, one that I like is this problem called the max cut problem. And the goal is to color the vertices in a graph so that you have as many, to color the vertices in a graph so that you have as many edges as possible going from a red vertex to a green vertex. So, this is a sort of canonical QUBO type problem. This framework is very general. You can encompass a lot of problems with this framework. Now, what's interesting is we've got a pile of quantum heuristics for solving problems once they are cast as QUBOs. Maybe most well known is this algorithm called QAOA, quantum approximate optimization algorithm, and sort of close relatives. It's sort of a whole framework of algorithm design. But one thing that's very commonly done right now is you take a real world problem, optimization problem, you write it as a QUBO, and then you throw quantum techniques at it. Something else that's very nice is that quantum annealers, these sort of special purpose quantum machines that I was talking about that can handle larger problem sizes right now, those are also very often designed to solve QUBOs. So there are a lot of quantum techniques out there for solving your problem once it is cast as a QUBO. Now, the caveat, and this is a very important caveat, is that just because you write your problem as a QUBO does not mean that a quantum computer is going to be good at solving it, right? There's a lot, this framework is very general. You can write lots of problems as QUBOs, and that's not always a good idea. Essentially, how efficient, essentially it comes down to this cost function, and in particular, the number of quadratic terms in the cost function. So this is just a sort of a first order idea, but what I want to, if you've got lots and lots of quadratic terms in your cost function, if every qubit, every I and every j sort of talk to each other, then maybe a quantum computer is not the most natural tool. If you've got just a few, then it might be. So that's the first estimate, but I just want to caution that, QUBOs are nice, they're a good approach, they're a natural approach to trying a quantum computer, but they might not always be the best idea. Now I'm going to switch gears a tiny bit and talk about some sort of quantum machine learning approaches, some more data science-y stuff. I'm not a quantum machine learning expert, so I'm going to do this at a very high level, and it might blend together a few ideas. So someone who has a quantum machine learning background and is in the audience might be upset about what I say next, and I encourage you to correct me, but I'm going to hopefully capture some high-level ideas here. So what are the ideas behind these? One sort of class of ideas called quantum encodings is I take classical data, so my pile of classical data that I want to process, and I have one of these parameterized quantum circuits, one of these simple quantum circuits that I sort of, with parameters that I tune classically, and I use that to encode my classical data into some very, very high dimensional space. So I take my classical data and I push it up in some high dimensional big quantum space. And then I measure that data and I collapse back down to some classical data on the other side. Okay, so I measure that circuit, classical data goes up into some quantum space, comes back down to classical data on the other side. What do I do with that classical data? Well, maybe that classical data that I get out of measurement, maybe it's labels for my data, right? Maybe I've just done some sort of categorization of my data. Or maybe I take that classical data and then I feed it forward into more machine learning approaches, right? Maybe I build some big neural net, and some of my nodes are quantum and some of my nodes are classical, and I try and process all my data in this form. And you can keep imagining things along this line. But in all of these approaches, the hope is that somehow by pushing into this high dimensional space and then collapsing back down, you pick up on some correlations, you pick up on some features in the data that you weren't going to pick up with a purely classical technique. And now the caution, the thing that I want to point out, is that this method starts with classical data, and it pushes that classical data up into the quantum circuit, but you've got the same bottlenecks. It's classical data that you're working with. Often, sometimes people think of quantum computers as tools for handling giant piles of data or large amounts of data. But these methods, these sort of quantum encoding methods, have the same bottlenecks as you do classically. You've still got to process all your data classically. You're going to push it up into this big quantum space and collapse it back down again, but it's not going to help you process more data than you could just using a classical technique. So that's a word of caution about some of these quantum machine learning approaches. Now, that sort of brings me to my next possible heuristic that I want to throw out there. This is also a machine learning approach, but I've separated it out because it has the advantage that it's sort of unique in that it can perhaps handle larger amounts of data. Why do you do that? Well, in this reservoir computing approach, I don't know if I said reservoir computing already, but in this reservoir computing approach, what you do is you take your classical data and you use it to tune interactions on your quantum computer. So your classical data doesn't become the input, but it determines the interactions. And then, just like in these encoding methods, you still measure the output and get a classical signal that you then post-process. But because here the data is being used to to tune interactions. You can have a whole series of these. You can handle sort of higher amounts of data than you can with sort of just an encoding style approach. The not giant amounts of data, but more at least. But it's a heuristic, it's another idea. It's not guaranteed. What it does sort of fit naturally, because you have interactions happening in various time steps to your data living on this quantum device, is that these reservoir computing approaches are usually applied to sort of forecasting or time series data, right? Where you have a whole amount of time series data and you feed that in interaction by interaction on your quantum computer, and then you measure out and you hope that you get some signal that you can use for forecasting. Okay. So that's it for the teasers and the samplers. And now last technical slide, but I just want to get maybe one step even more concrete and talk about some ongoing work that's sort of in this domain that I know a little bit about because I'm involved with it. And this is a project, ongoing research about quantum approaches to the unit commitment problem. And so probably there are lots of people in the audience who know more about unit commitment than I do. But my short summary is that unit commitment problem says I've got a collection of generators, power supplies in some network, and my goal is to figure out which ones to turn on and off and how much power to have them put out so that I can meet some predicted power demand while minimizing cost, right? Or something more complicated than that. Let's be simple and say cost. So I want to meet predicted power demands and I want to minimize costs while doing so. Okay. And now what happens if you try to throw this problem on a quantum computer? And so this is something we're doing right now. What's the near-term quantum approach? Well, the first thing you discover is that this problem is what's called a mixed binary optimization problem. There's binary variables, which say, is my generator on or off? And there's continuous variables, which say, how much power am I putting out from each of these generators? And now, because the quantum computers that we have today are so small, because you only have a few number of qubits to work with, what you find is that there's absolutely no hope of fitting these continuous variables onto a quantum computer. And so what you have to do is you have to come up with an intelligent way to sort of separate out a problem on the continuous variables and a problem on the Boolean variables, the zeros and the ones, and ask a classical computer to solve the continuous part and a quantum computer to solve the quantum part. And you want to make sure the quantum part is still interesting and hard, and ideally the classical part is easy. So that's sort of the first step that you have to go through. Okay, and then you've got now a Boolean optimization problem, just zeros and ones, and you can push that onto a quantum computer. And okay, now it's not exactly a QUBO problem. So there are some constraints and you have to think about those constraints, but you can sort of tweak these QAOA approaches that I was talking about earlier, these QUBO approaches, and get a quantum technique for solving this problem. So that's the real quantum mechanics piece of it. And that's also very interesting. And you can lean on research being done. There's a lot of active research in this sort of area. And then even once you've done all that, now you have a quantum approach, but you have to go back and say, okay, now I've got a quantum approach. I want to compare it against classical approaches. And I want to go out into the wild, into the real world, and find instances of this problem that are hard, that people care about solving. And there's a subtlety here, right? Because just because a problem is hard in the worst case doesn't mean that the real world examples of the problem are hard. Doesn't mean that there's an actual application of the problem where it's hard, where classical computers struggle. But you really want to try and put your finger on that. And then once you have that, then you throw your quantum techniques at it and just see what happens, right? You're not at this stage of quantum computing. You're just benchmarking an approach. So there's no guarantee, no promise that your quantum computer will outperform, but at least you're taking a swing in the right ballpark. And that's sort of if I wanted to, with a very broad brush, paint what projects look like right now, with just this as an example. That's sort of the flavor. So, okay. But I will stop there. Thank you all. And we'll move on to more of a discussion, more of a back and forth. So I'll throw back to you, Anu.
That was great, Adam. Really, really good. And thank you so much for that. You're a very good speaker, very engaging. You explain things well. I do think there's probably, I know quite a few people on the call that'll be keeping up with this. I think the James Van Leuven and Charlene Becky and Glenn Gordon and those people that are kind of in that data space will be picking up on things. And thank you for the electricity use case, because that was really good. I just want to let people know that the session has been recorded, and really apologies for the Eventbrite doesn't seem to populate your calendar with your meeting, so you have to go to your order confirmation and get the link to get in here. So I apologize for that. I think it was hard for some people to connect, and some people haven't been able to connect, so apologies again. But we do have the recording, and we'll be sending it out to all the registrants and putting it on our YouTube channel. What I wanted to say, and I can see that James has raised his hands, or just one hand. I want to put it out there to those that are listening from industry that I feel like one of the issues in industry is, like you were talking about the data and the complexities of it and how to get on top of it. I sometimes wonder whether it's like really like, how do we get a more visual, concrete understanding of what is this data? Like, where do I find it in the filing cabinet? What shelf is it on? How do I access it? What format is it in? And I'm not sure if that's the most important question, but I think as we go through this process, the other thing I'm thinking about is in industry, our members are hiring electrical engineers, power engineers, sometimes software engineers, but I don't often hear them hiring physicists or, computer scientists, which maybe is a change in the workforce. So that's another kind of topic we can get to. And I think maybe people can turn their cameras on now too, because we're at 32, and I think that's an okay group to, if you turn your cameras on. And James, I'll hand it over to you. That wasn't a question, Adam, that was just me rambling on. But James, you can unmute yourself and have a quick chat with Adam here, and try to be brief though, and stimulate some more discussion.
I'll do what I can. Thanks, Anouk. Nice to meet you, Adam.
Nice to meet you. Yeah.
Really enjoyed the presentation, and top of mind for me is areas of application. So you ended the presentation on one specific focus area, and within the community, what would you describe the frontier right now? What do people in your position, for instance, see as being the real cutting edge area of application that we can really sink our teeth into? Is it the utility space? Is that why you brought that example up, or do you see other things?
Yeah. I don't want to say there's a rift in the community, but I'll say there's sort of two schools of thought in the community. One says, maybe we're not going to get any interesting applications until we hit these fault-tolerant algorithms, right? So that says, sort of throw out all of these variational approaches, throw out these quantum classical hybrid approaches, and just wait, do the resource estimates, find the really concrete, strong applications of quantum computing, and get ready for those. So that's easy if you have a problem that at its heart involves quantum simulation. On sort of the more general framework, maybe it's things like this HHL, this matrix inversion, and finding applications of that. But there's a lot of caveats there. The other school of thought says, let's try, right? Let's try these near-term approaches. Let's try them at utility scale. And let's, that's exciting because it means you can talk, as the hardware develops, you keep trying, right? You try a problem with the hardware today, you try a problem with the hardware in a few years, you can handle bigger problem size, you can do more. I don't want to be too negative. There's some theoretical ideas out there, but this is really a space of heuristics and experiment and do the experiments and see what happens. So it's a frontier, but the in a sense, you just take an idea and make a swing and see what happens.
Okay, thanks.
Yeah. There's more I could say, but I'll stop there. And if that,
just fill your boots. Take it away.
Yeah. Okay, I'll say one more tiny thing, which is if you want an actual sort of theoretical question that we're struggling with right now, as these variational circuits get bigger and bigger, the problem of actually training these variational parameters is very tricky. This goes under the name of barren plateaus, especially on the sort of machine learning approaches. This is an obstacle that we see. So how to scale these variational circuits is an interesting problem. And then in any industry, in any domain, there's a lot of just concrete how to get a problem compressed enough that there's something interesting to throw on the quantum computer.
Right. Yeah.
That's another big one.
Great. Thanks.
Yeah, for sure.
And thanks for that, James. Is there anyone on this call that has kind of that's got a good idea of a use case from a utility side or from a building management system or a software, predictive analytics, anything? Is there anyone who wants to jump in and kind of give an example? Because we've got a mix of quantum technology providers on the call and a mix of decentralized energy the
Technology.
companies on here. So that's a technical term. Bleh. So there's a mix. So is there someone, I don't know if we've got anyone from Arcus, Hamid, I don't know if you're on the line, but just to give us a bit of a, just to connect the dots a little from deep in the data world to the actual use case.
Hi, Anouk. Yeah, I'm here. I'm listening and thinking. So
Is that Hamid?
yes, it is.
Ah, very good,
Yeah,
very
yeah,
good. Because I was actually wondering if the that distribution network, looking at the loads and managing the loads. And Glenn, I know you have it. You pretend you know nothing, but like that there's anywhere where you're dealing with a distribution network with a lot of loads that need to be managed, and how do you get that voltage stability? I'm making stuff up a little.
I can drop just a couple breadcrumbs if that's helpful. But don't let me stop anyone else from talking. I'll just say these are more easy starting points than necessarily the best idea. But I think it's nice to have a starting point, and then once you do that, you can find other applications. Anytime where you have an optimization problem that you're trying to solve approximately, so you've got an NP-hard optimization problem, but you care about approximate solutions. This is often a starting point for throwing a quantum optimization technique at it. That's what happened in this unit commitment example. Again, not a guarantee that your quantum will outperform or be useful, but it's of the right form to try. Anywhere where you're already doing machine learning, classical machine learning, and you think it's useful, then you can start thinking, you think it's useful, but you think it could be better. Then you can start thinking about introducing quantum somewhere along the pipeline. If you're already building a classical ML solution, it's not that much work actually to change out some of the parameters, at least at the conceptual level, to quantum circuits, to a little piece that is quantum, and incorporate that into the whole ML pipeline. So those are two easy starting points I can mention.
And maybe this is a good time to just hop into kind of what the next steps will be, because to be honest, Adam, it was really good, but I'm finding myself, there's a little gap between what goes on in our industry and with our members and the information I hear from them and what your presentation was. So we're going to try and figure out how to bridge that gap. And I think our next step is the discovery session, right? So what we're going to do is we're going to invite a group of decentralized energy industry stakeholders to a day session. And the idea is that before we get into that workshop, like Quantum City will be the partner that's going to help us with the data. But before we get there, we want to get some examples of the data. What data do you have? What format is your data in? What describe the complexity of it? And Glenn, you had a point, because when we sent out those questions yesterday, helping us define the problem. Like some of us don't even know what problem we actually have. So I think this discovery session is going to help us get to that point where we understand a little bit more about the opportunity here and how it fits with our decentralized energy businesses and daily operations. So I think that'll be exciting. That's sometime in April. And we'll send that out to you with the recording. We'll send you the, when we're going to get the discovery session planned. Could you tell us more about QGAN and then Spencer? So that was Tabby. And then Spencer's got, I don't pretend to know a lot about quantum computing, but I wonder how it would impact weather. Oh yeah, that's a good one. And
Yeah.
emissions, weather predictability and how to opt it. That's a good one.
Yeah, okay. I'll try and grab those two quickly. So QGAN I can address quickly because it's a little outside my area of expertise. So I can say I don't know much. But this falls under these sort of very quantum classical machine learning approaches, right? Where you take your standard classical architecture, your standard classical approach, and you replace some pieces with a parameterized quantum circuit and hope that accessing a larger space gives you more, a more performant algorithm at the end of the day. So that, that's a very general statement that applies to a lot of quantum machine learning approaches. It also applies to QGAN. But there's subtleties there that I actually don't know, but would be happy to talk, happy to read about and then talk more about. Yeah, weather predictability, optimizing solar wind generation. Yeah, absolutely. And I know some work in this space, and maybe I'm getting my signals confused because maybe they're actually looking at financial markets and thinking about solar wind generation. But again, using this reservoir computing approach, right? So time series data, you feed it into your quantum computer, and then you hope to get a signal out that you can use for prediction. So that certainly fits into the reservoir computing paradigm. Yes.
Yeah, and I think that's one that quantum computing is going to be all over. And emission, we've talked a bit about the emissions measurement side of things, especially if you want to do life cycle analysis from multiple places. I think that's another interesting one.
Yes.
I had another example in my head and I can't remember what it is now. I think we're at 3 minutes before, so I think we can kind of start wrapping up and go into our next step. So as I said, the next step is for Quantum City and DEC to co-host a discovery session with industry stakeholders that have potential use cases. So we'll get primed for that. We are working towards the quantum edition of our Energy Innovation Challenge, which will allow us to actually get some funding to support pilot projects. So if we can get kind of the, IBMs and D-Waves of Canada working, and if we go global, we'll get even more participation. But we want to bring some of the quantum technology providers, hardware and software solutions to the table to help our industry get on top of this on the quantum computing, quantum sensors, and cryptography. So creating a more secure microgrid or virtual power plant and protecting our data, et cetera, et cetera. So that's the discovery session. There is also on November 5th and 6th, Quantum City's hosting Q Connect in Calgary. So in our follow-up email, we'll send you information and a link to register for that. And then November 20th and 21st, the Decentralized Energy Forum is in Quebec City, and our theme this year is Energy and the Quantum Advantage. So a lot of people on the quantum technology side of things on this call will be there. We'll be hopefully digging deeper into the discovery session, like some of the use cases and getting some real, nuts and bolts out there for that. Did I miss anything?
Hey, Anu, can I just say one thing?
Yeah.
Because you're right. You're wrong. I mean, I don't know anything about it. But one of the things I think for that discovery session is, when I was learning French, there was almost always a translated word in English. And so a lot of it was, this is the word in English, learn it in French. But then when we were learning Mandarin, we come across a lot of things where there's just no translation for it. And I think one of the struggles that I have with quantum computing is I'm constantly trying to translate what you're talking about into the language, the classical language, and say, okay, well, this is what that is. This is how it is. And I think a lot of people, that's how we learn. It would be good, I think, as part of that discovery session to identify those areas. Say, don't try to translate this into your understanding of binary classical computing, because there is no translation. It's completely different. And it may help sometimes. I know some of those things were like, okay, don't try to think of the word, but try to think of what that is. And I think that might help someone like me, because I really am struggling with a lot of this. And so when you say, what would you apply quantum computing too, you know, we always sort of go to that, oh, this is just a way to brute force stuff, and it's not, right? And so it's that, you know, when you, and as you're going through it, Adam, I think you did a very good job, because at least I started to understand, okay, I don't think there's a translation for that. I don't understand it, but I'm not going to sit here and try and say, well, how would I convert that into classical? So it would be good to have those kind of concepts up front to say, before we get into this, don't try to translate this into what you understand, because this is totally new for people like me.
Yeah, I think that's actually very helpful for me too. I'm gonna throw just a tiny thing on, just because we're talking about discovery sessions. I'm gonna add, you know, easy for me to say from the theory point of view, but I mean, I think that, you know, there's often a worry about figuring out the right problem for quantum in a discovery session, and I mean, the chances, you know, that any of us get the right problem the first time is pretty slim. You know, like I think find it, you know, the first thing that you try and use a quantum computer for is probably not going to be the end application where you find where it's actually a useful to your industry. So I mean, I always like to think of it as, you know, it's a chance. I think someone said this in the questions too, to get us all in the same room and talking, and, you know, maybe we come up with something and try, and we figure out that that's not the best use of a quantum computer, but we've all learned something, and we have that communication open, and the next thing we try can be more informed. So I just, you know, take the pressure off a little bit. You know, it's not about finding the perfect one first time so much as it is starting the dialogue.
Yeah, no, that's good, Adam. And then I see Alexandra had a comment about public policy, and from what I understand, there is movements in the policy space, and it's mostly around standards, conformity, and security, I think, is the most active, like the cryptography and the use of cryptography for heightened security. Is there anything else you want to add on the policy side?
No, I think you nailed it in terms of the crypto side of things, which I didn't talk about, is sort of the most pressing public policy. You know, there's incentives for industry and researchers to be working together. Quantum City is born of some of these incentives. So, you know, there's support for industry moving in this direction. But that's not quite public policy.
You're right.
Yeah.
All right. All right. Well, I think that's it. That concludes our session. Thank you so much, Adam and Quantum City. I'm looking forward to working more on this and learning more.
And so how do we, because I'm going to have to watch this 16 times, but how do we find the recording of this?
We're going to send it to you. We're sending out the
you.
recording to everyone who registered, because the people had problems joining as well. So we'll send it out and get it up on the YouTube channel.
Hey, Anouk, I just wondering if I could just comment on something. It's just
Yes, Charlene.
random, because my brain isn't quite conceptualizing everything about the conversation so far. But when I worked in reservoir geophysics, we did a lot of predictability of reservoirs and edges of reservoirs, and you know, characteristics of reservoirs. And what we did is a lot of, like, what you nowadays call kind of machine learning and Monte Carlo simulations, different types of simulation techniques and that type of thing. So what I'm thinking could be, you know, I'm not sure how this would all apply, but what I'm thinking, like, we would put in a ton of data, you know, and make some sense of what we saw in the data itself. What I'm thinking, I was kind of throwing it out there, but with the new REM markets, we have to do day ahead predictability of cloud cover, and, you know, however that's going to work into, you know, predicting power out of facilities, and power generation. I'm thinking this could be a very important application of quantum computing, but again, we'd have to see if, like, I don't know if it's robust enough to take that amount of data in, because, you know, we'd have to look at years and years of cloud data and sun data and everything else, and see if, you know, if it's too complex for something like that. But it's something like, you know, that predictability is going to be huge in this industry. Well, in Alberta anyway, because we're being pressured to do these types of things. But maybe that's some way to apply it. I don't know. Just throwing it out there.
No, yeah, that's awesome. That sounds like a very, very great starting point. And ties, you know, there's a related, you know, one of my pitches is, you know, something like this, where it sounds like probably you're already going to be building or investigating classical machine learning techniques. You know, I'd love, to be in the room just to hear it, to see if there's points where you can put in quantum, right? I mean, it's like you're probably right that you're dealing with so much data. It's not all going to fit on a quantum computer, but if we can find it's a good starting point. Maybe you can find a piece of it that does make sense to put on the quantum computer. You know, a way to
Yeah.
integrate quantum into the solution.
Yeah.
Like
And I
bringing
can,
the accuracy into it is the biggest thing. Like the predictability and the accuracy, right, is going to be the biggest thing, because if we don't meet our, you say you're going to predict so much power generation over 1 hour following day.
Yeah.
How accurate is that, right? Like, maybe quantum is a better way to approach it than Monte Carlo or something like that.
Sure. Yeah.
But I
super.
think it could all apply. Who knows, right?
Well, we'll get you in the room for the discussion, Charlene.
Yeah, if my
Hey.
brain doesn't implode. Okay, great.
Thank you again, Adam, and everyone have a good afternoon.
For sure.